Prompt engineering is a rigorous science of constraint. To achieve reliable, production-ready results, the workflow shifts from writing conversational requests to designing a precise operating environment for the model. Consider this case study. We need an AI to analyze a foreign language car accident report. The document contains 17 rows of checkboxes on the left and a hand-drawn sketch of the incident on the right. The goal is to extract the facts and determine which vehicle is at fault. If we provide these images to a model with a baseline prompt, it fails. Because it sees Swedish text and a specific document layout without any provided context, it interprets the visual data through its broadest training associations and identifies this as a skiing accident. This failure happens because the model is operating without guardrails. It attempts to resolve the ambiguous Swedish text and the document structure by defaulting to its highest probability guess, which leads to a confident hallucination. Our first iterative fix is to provide a semantic anchor. By assigning the model the specific role of a Swedish insurance claims adjuster, we force it to reinterpret those visual cues, like the street names and the form's layout, through a vehicular lens. We then add a strict behavioral rule: do not guess if the data is unclear. With this professional context in place, the model stops seeing a skiing trip and correctly identifies the car accident. However, the do not guess constraint creates a new hurdle. Because it still lacks specific knowledge of the form's internal logic, it refuses to assign fault, citing low confidence. This reveals the limitation of behavioral behaviors alone. While a persona stops the model from hallucinating, it does not provide the domain knowledge required to decode the document structure. The model is now cautious, but it is effectively stuck. We resolve this by injecting static domain rules into the prompt. Using XML tags, we build a form structure guide, mapping the definition of each of the 17 rows and 2 columns directly to the model's understanding. Providing this structural data allows the model to map the visual locations of checkboxes to their specific meanings. It no longer needs to guess what a mark signifies. It simply matches messy human inputs against the definitions provided in the prompt. Even with the right definitions, the sequence of analysis determines the quality of the output. If the model begins with the subjective sketch, it struggles to find a baseline. We must enforce a strict order of operations, directing it to process the factual data of the form first. We update the prompt to force a systematic evaluation. The model must list every finding from the checkboxes and build a factual summary before it is allowed to interpret the unstructured drawing. Establishing this factual context first is essential. Once the model has locked in the data from the form, it has the necessary framework to accurately decode the subjective details drawn in the sketch. The prompt is now highly accurate, but the output is a dense block of reasoning. While this is useful for a human, a data engineer needs a clean, predictable variable to store in a database. Pause the video here. Based on our use of XML so far, how would you constrain the prompt so that only the final verdict is isolated for extraction? The solution is an output formatting constraint. By commanding the model to wrap its final decision exclusively within a designated XML tag, we can programmatically separate the final answer from the model's internal reasoning. The engineered prompt now delivers a successful extraction. The model uses the checkboxes to frame the sketch, identifies the at-fault vehicle, and isolates the result within our tags. To optimize this further, you can utilize models with extended thinking capabilities. These models provide a visibility scratchpad, showing the logic used to reach a conclusion in real time. Analyzing this scratchpad allows you to see which logical steps were most effective. Bake those successful patterns directly into your system prompt for a faster workflow. Reliable prompting follows a 4-step checklist. Establish tone and role constraints, inject domain rules via XML, force a strict order of operations, and constrain the output formatting. Predictable results are the product of structural environmental design. By refining these 4 layers, you move an AI from a general assistant into a reliable tool for technical data extraction.